Any questions before we get started about anything? Kind of just barreling towards the end of the quarter here. So I think we have one more lab next week after this week, and then the lab final will be Thanksgiving week, so the Wednesday of Thanksgiving. And so, of course, I'll just remind you guys to register. So I think registration opened up today to everybody now. So hopefully everybody can register if you haven't already, and then just let me know, and I'll tally up your extra credit points for the end. Oh, and then one more thing. So we're going to have a guest speaker. So I did this thing last year, and it just so happened that this year my 200 level class, I have a student whose sibling is in a graduate program in chemistry. And so we're going to have her give a talk. So that's going to be December 2nd. So that's a Friday at 1 p.m. and tentatively in HEC 112. That's like the big lecture hall. But if y'all come in and also just listen to the talk, then I will add extra credit points for that as well. And then if you can't make this time, I'll record the lecture or the talk, put it on Blackboard, and then if you watch it later, just send me like a sentence or two, what'd you like about it, then I'll also give you the extra credit. So extra credit opportunities, it goes through the end there. And I'll make an announcement about this once I'm sure that we'll be in this room. All right, so let's continue with our pressure chapter. And so now we'll look at Dalton's law. And so Dalton's law just says that the total pressure of a gas mixture is the sum of the partial pressures. And then again, we're going with our kinetic molecular theory. So we're saying, okay, we're ignoring all intermolecular interactions. So the particles have negligible size. So again, we don't care which molecule's physically bigger when we're just thinking about this. And then we're not, again, not thinking about those intermolecular forces. And so with this kinetic molecular theory, then all the gases, the pressure is additive. And so particles of different masses have the same average kinetic energy at a given temperature. And then the average kinetic energy is the same, so the total pressure of the collisions is the same. And so anytime then we have a mixture of gases, the pressure of a single gas in that mixture is called the partial pressure. And so you can calculate it by either knowing a fraction of the mixture and then the total pressure, or you can know the number of moles in a gas in a given volume and then use kind of your PV equals nRT and get the pressure that way as well. And so again, the sum of the partial pressures of all the gases in a mixture equals the total pressure. So that is Dalton's law of partial pressures. So again, just the total pressure is your pressure of gas component 1 plus your second gas plus your third gas, all the way up to however many gases are in your mixture. And so let's run it back. So in this case, so let's just look at how this would work. So air is at 1 ATM. And then, so do y'all know the composition of air? What's in air? So there's probably like a small amount of water. I don't know, that would probably be like 1%. Probably like a little bit of methane. So a lot of O2. So how much O2? Any guesses? It's actually not majority O2. 21%. So 21% oxygen. Methane is probably negligible. And then what's the main component of air? So nitrogen. Any guesses on what nitrogen is? So 78%.
I'm not that smart, it was just a question.
I was like, you're rocking it. Well, that's great. And so if you know all of your percent compositions for this, so we can tell then the partial pressure. So if we know the fraction of the mixture, we know the total pressure, so then you can just multiply the percent by your total. So this means that nitrogen is 0.78 atm. Oxygen has a partial pressure of 0.21 atm. And then any of those smaller gases, right, they would be, so move it over, so 0.01 atm approximately if it's 1%, so something like that. Then you again add them all up to get back to that 1 atm. And so this is just a derivation of it. And so all they did was set pressure. So we started with PV equals nRT. Then they rearranged pressure to just be RT over V. Then all they did in this next step was to kind of pull out the moles. So you can see that, yeah, it's more dependent on just the moles. And so they pulled that out to be your mole 1 plus mole 2, etc., times RT over V gives you back to your pressure. And so again, that just proves why it's additive and is just dependent on the amount. So proves additive. So that's really all that's saying. So you could figure out the pressure either of each of these individual mole components, multiply it by nRT, divided by V to give you the pressure, or you could total up the total number of moles and that would give you the same total pressure. So the other way we express these ratios of gases are with this mole fraction. And so all this is our ratio of our partial pressure in a single gas over the total pressure. So our partial pressure of component A over our total pressure. You could do the derivation. It would be equivalent also to the amount of moles of your partial of the component A over the total number of moles. So just the ratio of the moles as well. And so this means that we could find the total moles in our system. And then if we wanted to get the mole fraction, we get the moles of whatever component we're interested in, and then just divide that component divided by the total gives you the mole fraction. And so the mole fraction should always be less than 1. And so again, once we get this mole fraction, we can just multiply it by the total pressure to get the pressure of that individual component. And so like we saw previously, so nitrogen was 78%, multiply it by the 1.0 atm, and we get 0.78 atm, and then pressure being additive. So these are the three main components, so nitrogen, oxygen, argon, but like y'all mentioned, of course, air has many other gases, so carbon dioxide, methane, water, neon, hydrogen. All right, so now we're going to kind of shift gears a little bit, and now we are going to start thinking about the intermolecular forces and what does dictate kind of these phase changes. How can we tell what state a molecule is going to be in? And so we've seen this before, so this is just our generalization. What is a phase change? So we said that we start off as a solid, and I'll just repeat this, so fixed volume, fixed shape, So this has the least amount of energy. And then you start adding heat to it. And so we add enough heat that the molecules can slide past one another, but they still have the fixed volume. Then we continue adding more heat. We get them into our gaseous state, and then again, no volume, or no fixed volume, no fixed shape. And then highest energy, of course. And so let's look at, so what really dictates this? And again, you know, how come methane is a gas at room temperature versus water? How come water is a liquid at room temperature? So let's try to ask or answer all these questions. And so now we do want to look at the attractive forces that hold matter together. And so these are intermolecular forces. And so this is going to be between molecules. So that's going to be like between two molecules of water. What's the attraction between them? And so this is different than intermolecular forces. Intramolecular forces. So this would be within a molecule. So what keeps it bound? And so this is like the covalent bonding, all that single bond. So those are intramolecular forces, so within a molecule. And we're looking at intermolecular forces, kind of like your interstate highway is between different states. Same thing with our intermolecular forces. It's between molecules. And I'm really emphasizing that because when we talk about, you know, adding heat and breaking these bonds, I want to make sure that we're talking about breaking intermolecular forces, because it's easy to just throw out, oh, we're breaking bonds, but we're not breaking covalent bonds, so that would require a lot more energy. But we're just disrupting these intermolecular interactions. And so now let's see, well, what holds particles together? And so all attractive forces between particles are electrostatic in nature. We've seen that. So, you know, think back to our ionic compounds. That's electrostatic, something positive and something negative holding it together. So we have to have some sort of charge differential to get some sort of attraction. And so that means that the strength of the attractions between the particles of a substance determines its state. So if it's really attracted to each other, then it's probably going to be a solid or a liquid. If they have really weak intermolecular forces, right, they're not going to want to be together, so it'll be a gas. And so at room temperature, we see that moderate to strong attractive forces result in materials being solids or liquids. And so that's kind of thinking of more covalent compounds at this point. So we mentioned, right, those ionic compounds, those always tend to be solids. But we're trying to answer, well, what about these covalent compounds? You know, what dictates what state they're in? And so again, the stronger the attractive forces are, the higher the boiling point will be, and the higher the melting point. So then that kind of makes sense. So just think about it. If you have strong intermolecular forces, right, you're going to have to take more energy then to break those apart and either get it into the liquid state or all the way into the gas state. And so these attractive forces do vary in strength. And again, we'll go over what dictates their strength. And it also depends on the kinds of particles. So we'll look at kind of geometries that make these attractive forces either favorable or not favorable. And of course, the stronger the attractive forces between particles, the more the particles resist moving. And so again, we mentioned, so no material completely lacks particle motion. There's always our electrons moving around. There's always vibrational, wagging, stretching of our molecules. So there's always action going on. And so again, we'll go over the strength of intermolecular interactions. So boiling a liquid requires that you add enough energy to overcome all attractions between the particles. So again, we're not breaking those covalent bonds. So you're not heating, if we're heating up water, we're not breaking that OH bond or anything. We're just disrupting those intermolecular forces. And so that means the higher the boiling point of a liquid, and normal just means like at STP basically. So that's 1 ATM, you know, our standard conditions. STP is 0 degrees Celsius, but normal, that's going to be, that could also be room temperature. And so again, the higher the normal boiling point of the liquid, the stronger the intermolecular attractive forces. And so we had mentioned, well, why are molecules attracted to each other? We said that they have to have some sort of electrostatic interaction. So again, that's attractive forces between opposite charges. We've seen the extreme of that from ion with a cation and an anion. So again, two charged ions, then they come together to form our ionic compound. But now we're going to be looking at, well, what about what happens when you have the end of a polar molecule that's attracted to the negative end then of another polar molecule. So looking at those dipole moments. And then we'll even look at, so even nonpolar molecules will have these temporary charges. And so the other thing is, so a larger charge means a stronger attraction. And so that you can compare that of a sodium plus charge versus a magnesium 2 plus. So the magnesium 2 plus would have a stronger attraction. So of course with these charges, we'll also see this related to polarity. So if you have something very polar, if you have like a formal charge located on the molecule, like with nitrate, where that formal charge is on the oxygen, that's going to have a strong attraction. And then you want them to be closer together. So the closer together, that means you have a stronger attraction. Of course, longer distance just means you have a weaker attraction. And so again, we're just looking at the intermolecular forces. And so the intermolecular forces are small relative to the bonding forces. And that makes sense. So that's why we can break those intermolecular forces more easily compared to the intramolecular. So now we'll look at kind of the weakest of the intermolecular forces. So this is the dispersion forces. And so you might also see the name, they could be called London dispersion forces. Or the other term that you'll see is van der Waals. And so every molecule has these van der Waals forces or these London dispersion forces. And so they are brought upon by the fluctuations in the electron distribution within atoms and molecules, resulting in a temporary dipole. And so let's see, well, what do they mean by that? And so here we're just looking at a collection of helium atoms. And so there's our helium, so our nucleus, and then of course our electrons are circling around. And then so right now what we're looking at is we're just looking at this instantaneous snapshot. And basically it's saying, what if it just so happens that on this helium, right, these two electrons just happen to be on this left side. And so that gives us a very temporary negative charge here. Then we have our temporary partial positive charge on our right side. And then what if it is next to another molecule of helium that kind of does the same thing, where you have your two electrons on one side, again giving you this negative electron density, and then that would be attracted, at least temporarily, to this partial positive region. And so it kind of goes down on this line. And again, it's just that temporary attraction. So then, of course, these electrons will keep moving, and then it will not have the same configuration, but they will keep moving around. And so it's just that temporary dipole that's created momentarily that keeps them attracted to one another.
So some of them can change from polar to non-polar, is that?
Kind of, except, so we'd still consider helium like nonpolar, right? And so this is especially true for like nonpolar molecules, that the dispersion forces are going to be really relevant. But yeah, it's just like a temporary effect where it's just like those electrons just happen to be more on one side, and then there's just so happens that the other one has a region of less electron density, so then it's going to be attracted in that instant. Yeah, so it's very fleeting, right, moving around, so it's not a long-lived dipole moment like, you know, we've looked for in the past. It's just a very temporary thing. Oops. And so like we saw with the little diagram, the region with excess electron density has a partial negative charge, and then the region with depleted electron density has a partial positive charge. And again, the attractive force that is caused by those temporary dipoles is called those dispersion forces. And so as the temporary dipole is established in one molecule, that tends to kind of help also induce a dipole in all the surrounding molecules. But again, it's still temporary, so it's still fleeting as those electrons circle around. And so all molecules and atoms have dispersion forces. So every single one, including, of course, the polar ones, we'll just find that the polar molecules are influenced more heavily by their other intermolecular forces. And then so looking at how size would affect the London dispersion forces. So as we look, so as molar mass increases, of course our electrons increase. That means that we get a larger cloud, and so the strength of dispersion forces increases. And so if we look at this little chart, that kind of highlights everything most clearly. So we can look at helium. So obviously it's the smallest, has the smallest molar mass. And then if we compare the boiling point, so look at the boiling point of helium, 4.2 Kelvin. So that's really, really close to absolute zero. So extremely low boiling point. So you can also tell, right, they have really weak intermolecular forces since you have to cool it down so much for it to be liquid, to condense. So that's pretty crazy. But then as we go up in size, so we're going down the noble gases, so neon, argon, krypton, and xenon. So as we go down, so now xenon has a mass of 131 and then a boiling point of 165. And so we can tell, right, they have a little bit greater attractive forces, so there's just more area, more surface area too, that helps. And so it's just larger and has greater attractive forces. So again, we can see that in that boiling point trend there. And so similarly, it makes sense that the shape would have an effect, so how well can those molecules pack together? And so if we're comparing, so now we're comparing, pentane versus neopentane. And so why we want to look at this, as so pentane, they both have the same formula. So notice they have the same mass. And so their formulas are both C5H12. They're just in different arrangements. So if you can tell, the pentane, so 1, 2, 3, 4, 5, looks something like this. So this is how, same representation, just a straight chain alkane. So 5 carbons, and then all of these have little hydrogens on them. And then so we can think about how it would pack. And so comparing, thinking about that surface area for interaction, and they could even kind of pack in, something like this, or they have a lot of surface area there for attraction. And then if we compare it to neopentane, so neopentane is different in that it has a carbon in the center, and then all these carbons around, and then all the hydrogens. And of course, this has a tetrahedral geometry. I just didn't draw it very well. So it kind of has this ball structure. And if we're trying to think, well, how would that interact? So of course, we have a much smaller area for interaction and also just not very good packing. So that's a nice thing, or that's what happens with these long chain alkanes, is they tend to kind of stack and pack upon one another. So that gives them a lot of surface area for interaction, while the neopentane, right, there's not a lot of surface area, so really small. And so if we're just trying to compare, well, what's the difference between them? What dictates their boiling points? Well, their masses are the same, so that doesn't have an effect. So then it must be their geometry. So we see that pentane, so still a pretty relatively low boiling point liquid at 36 degrees Celsius, so you just gently heat that. But if we look at neopentane, so it has a boiling point of 9.5 degrees Celsius, so that is lower than room temperature, so that would be a gas at room temperature, so that would be difficult to work with, versus pentane, where it's a liquid at 36 degrees for its boiling point. And so we can see this trend, or at least our mass trend, reflected in our boiling points of our alkanes. And so as you might imagine, so now we're just comparing all these straight chain alkanes. And so the boiling points rise with increasing molar mass. And of course, you also have better packing. So of course, nonane has 9, and that can pack pretty nicely. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Just want to make sure I counted. So those can stack quite nicely. And so octane, right, that's fuel. And so all that stacks pretty nicely. And then, of course, you notice as they get larger, then their boiling points also increase. And so that's mainly due to the mass effect, but again, you also have that increased surface area as well. And so just a note, so of course, any branch chains for comparison would have lower boiling points. So you could imagine, so if you had, right, any sort of branching, so that could affect it. And it just depends as well, like how branched is it? So that would be kind of judgment calls. So obviously neopentane was kind of the extreme, but you may just have, kind of one sort of branching like that. It would be lower compared to the comparable carbon. So this is 1, 2, 3, 4, 5, 6 carbons versus hexane. So versus a straight chain, so hexane would have the higher boiling point compared to the branch there. Oh, question?
Are we gonna have to memorize the boiling points, or is there kind of a list we can look at, or?
You would just be, you'd be expected to predict trends, basically. So this one question I could give was just the example I was giving. So 1, 2, 3, 4, 5, 6. So it'd be which has the higher boiling point, and then, okay, well, I know the straight chain should have the higher boiling point. But I would never ask you to give me a specific boiling point, just which one has the higher one. So now let's look at the other attractive forces. And so our next one are going to be these dipole-dipole interactions. And so these are interactions between polar molecules. So anytime you identify a polar molecule, then you look at it, and then you also can say, well, if it's polar, then I know it's going to have some sort of dipole-dipole interaction. And now this makes sense since polar molecules have a permanent dipole. So unlike our nonpolar molecules which only had that temporary dipole, the polar molecules always have a dipole. So they always have some sort of unevenness. Remember that unevenness, and electron density. Right, so all we're saying is one side is always going to have a negative charge on it, or partial negative charge, and the other side of our molecule is always going to have a partial positive. And so we've kind of looked at this previously, and we'll get more of a taste for it now, but a bond's polarity and, of course, the molecular geometry determine the substance's polarity, and the charge separation is referred to as a dipole moment. And so now we're looking at acetone here. And so acetone has a permanent dipole, so we have this CO group here. And so that oxygen is going to carry a lot of that electron density. So we also mentioned oxygen is extremely electronegative. And so if we were to look at the electrostatic potential map, you can see the area of high electron density is shaded in red there, and then they use this blue for the partial positive charge. And so when it orients itself, it would orient itself, of course, with the negative charge kind of facing your partial positive charge. They would be attracted there. And so the permanent dipole adds to the attractive forces between the molecules, and of course raising the boiling points and melting points relative to nonpolar molecules of similar size and shape. So let's see what they mean by that. So now if we compare formaldehyde and ethane, so this could be another exam question. And so the first thing you would look at is, well, are their masses the same? And so in this case, yes, their masses are really similar. So if their masses are really similar, then we can predict that they have the same amount of London dispersion or van der Waals forces. But then looking at their boiling point, so their boiling point is -19 versus -88. So what accounts for this huge difference, even though they're both small molecules? And so we see that this must be due to its polarity. So ethane, right, this is completely nonpolar. So just the H bonds, no dipole moment anywhere, no very electronegative elements. So this is nonpolar. Versus formaldehyde, where now it has that CO group here. And so again, that oxygen is going to be really electronegative and have that partial negative charge there. So again, that partial negative is on oxygen, and carbon partial positive.
Do non-polar molecules usually have overboiling?
Yeah.
Okay.
And so that would be a big hint. Like if you see a low boiling point, then you want to check maybe it's nonpolar. And so that's what dictates the difference. So on an exam, I might ask, which one would have the higher boiling point? And so in this case, you would recognize that it should be formaldehyde, again, since it's polar. And here's our other chart. So if you remember, you can look up the dipole moment of substances on Wikipedia if you ever need a little guide. to find, where's the dipole moment here? That's funny. For some reason, Wikipedia doesn't have a dipole moment of acetonitrile. Let's try another one. All right, well, while I try to find some dipole moments, so if we look at this chart, this is just helping us, again, kind of put some numbers with this chart so we can kind of compare polarities and then also compare the boiling points. And so first of all, we're looking at this selection of molecules since they all have really similar masses. So they're all around, 44 or so, roughly. And so if we look at propanes, let me zoom in a little bit more. So propane, that's going to be completely nonpolar. So we look, it has a dipole moment of 0.08. So again, basically nonpolar. And so it has a boiling point of around 225 Kelvin or so. And then as we go to the right, we just slowly start increasing our dipole moment. And so now this is dimethyl ether. So this would be really similar to ether, so diethyl ether. So this is just with one methyl group instead of two on each side. And so notice ethers are only kind of slightly polar. So they have that oxygen in the center. And so again, your electron density is located there in the center, but then the sides are going to have your partial positive region. And so it has a slightly higher boiling point. And then so continuing on, so ethylene oxide, again, same mass, but now the ethylene oxide is a little different. So if you can tell, the ether is like this, and then this oxide is more of a pronounced shape like this, so it has more of a triangle bond, I guess, for better words. And so that's more in a fixed shape like that, and so since that oxygen is kind of more protruding out, that makes it a bit more polar, and again, it's just reflected in that dipole moment, so 1.89. And then so continuing over, so we see the aldehyde, so now it has kind of one side is more polar, and so it has an even higher boiling point, so now we're getting close to 200 Kelvin. And then so looking at acetonitrile, so now it's the most polar, so it has that nitrogen group on the end here, so very uneven, has a higher dipole moment, and then of course has the highest boiling point. And so, again, just so you can remember, so I've looked up acetaldehyde, and so in Wikipedia, it also it reports the dipole moment for this substance. So you could look up the substances you're interested in, compare their dipole moments, compare their masses, and then kind of order them. And so another comparison, so looking at acetone, so acetone is similar to formate. It just has methyl groups there instead of hydrogens. And so we could compare, so it's 2.91 for the dipole moment for acetone, so that's going to have a high dipole moment. And then just comparing, right, its boiling point is going to be 329 Kelvin, so a little bit higher mass than what we were just looking at. So you can kind of see where acetone fits in then on this chart. So we were looking at 46 mass, acetone is 58 with a dipole of 2.91. Why aren't you scrolling down? Wow. So that's pretty similar to acetaldehyde here. And so again, it has a slightly higher boiling point than acetaldehyde, given that higher mass of acetone. I'll just write in acetone, boiling point. Trying to find the Kelvin boiling point. So 329 Kelvin and a mass of 58 grams per mole. And I'll put in the dipole moment, so 2.9. So again, you can always go to Wikipedia, right, check your dipole moment out, and then that would help you order your compounds of which is going to be the highest boiling point versus the lowest boiling point. So now the last attractive force, or at least the main attractive force, is hydrogen bonding. And so this is kind of a special case of a dipole-dipole interaction. And so hydrogen bonding occurs in these very specific scenarios. So when you have an electronegative atom bonded towards hydrogen, it strongly pulls the bonding electron towards it. And so hydrogen, right, it just came with one little electron anyways. And then when it gets bonded to oxygen, nitrogen, or fluorine, so highlight this because it's only with these. So it's only when it's oxygen, nitrogen, or fluorine bonded. Then those three atoms are so electronegative that it essentially strips hydrogen of its electron. And so that's what it says here in this line. And the term that they use is de-shielded. So that just means, again, that hydrogen is essentially totally exposed. But what that does is creates a very strong positive charge. And then, of course, you have your strong partial negative charge on either your oxygen, nitrogen, or fluorine. And you get this very strong hydrogen bonding. And so hydrogen bonding is the strongest attractive forces, at least of the three main ones. So the three main ones, again, are just the dispersion, dipole-dipole, hydrogen bonding. And so hydrogen bonding is the strongest of those three at least. So we're just comparing those three. And so if we look at both our kind of space filling and electrostatic map, so this is probably HF here. So of course our hydrogen. And so I like the electrostatic potential map better, so we can really see, right, hydrogen got stripped, so it's all blue. So it has that partial positive charge. Fluorine, of course, is taking all the electron density, and we can see that with that big red cloud here. And then it's going to orient itself, of course, with our partial negative charge being oriented next to the partial positive and continuing on. And so if we take a look at water and ethanol, so this explains why they both have very high boiling points, again, relative to the molecular weights of these compounds. So ethanol just has the OH group on it. So ethanol is 2 carbons. Oops, so 1, 2 carbons, and then the null is for our alcohol group, so our OH group on there. And so again with that, so I'm going to redraw this a little bit better. And so oxygen already has those lone pairs on it still, so that of course makes it electronegative. So if we look at this little drawing here, right, the lone pairs are going to be oriented over in this direction. You can see that with our red electrostatic potential map. And then we can draw our partial positive charge, so oxygen pulling all that electron density up towards itself. So there's our partial negative, partial positive charge. And then, so if we look at this depiction here, or this electrostatic map, again, we see how it's oriented. So that hydrogen is making a hydrogen bond then with that other oxygen. So again, notice how it's bonding with the other one. So this is the hydrogen bond, right, between molecules. So between your hydrogen of one ethanol and between your oxygen of the other ethanol. So that's your hydrogen bond, that again, your intermolecular forces that keeps them bonded together. And so this is just another little depiction of that same hydrogen bonding interaction. And let's actually get a picture. And so again, water does that same sort of thing. Let's get a picture. And so again, water will do the same sort of formation. And so if we're looking at this, so we have all our individual molecules of water, but then they're all hydrogen bonding together. And then if we think about ice in its solid form, so it makes these defined structures, and then of course makes it less dense than water since it takes up a lot of space. But then if you look at how it's oriented, so we have our hydrogen here is oriented towards the next oxygen, and so they're all hydrogen bonding together. So again, here we see a good hydrogen bond. So there's our molecule of water, then our hydrogen attracted to that other oxygen. And so other things we can kind of analyze in this, actually and we'll look at, so what's the boiling point of water? You remember? So this one we should know. Yeah, so 100 Celsius. So that's our standard. And so what's the mass of oxygen? Almost, or sorry, I should have, mass of water. I don't know, I think I said mass of oxygen. So sorry, what's the mass of water? And so our molecular weight, so 18 grams per mole. And so right away, this should look a little funny. So what we were just, compared to all the other compounds we were just looking at, so if we go back. So something with just completely London dispersion forces, so comparing neon. So neon's at 20 grams per mole, but it has a much lower boiling point. And again, all that is just due to those intermolecular forces. And of course, water is also special in that it has two instances of hydrogen bonding, right? So we have two hydrogens, so then we have two hydrogen bonding possibilities. Versus, so if we compare that to ethanol, so do you think the boiling point of ethanol will be higher or lower than water? So lower, so that's a good guess, and you're correct. So the boiling point of ethanol is actually 78 degrees Celsius, and so that was confusing. So ethanol, right, is slightly larger, so I'll give you the mass. So the molecular weight for ethanol is 46, but ethanol only has one hydrogen bond. So we only have one H there that can bond with another OH. And so just that little factor of one bond versus two bonds means that water still has the higher boiling point, even though it is the smaller molecule. So water is really special in that sense. All right, so let's look at some more comparisons. And so just to emphasize, so again, we keep saying, so hydrogen bonds are very strong intermolecular forces. So they're the strongest, stronger than the dipole or the dispersion. And so like we've already seen, so substances that can form hydrogen bonds will have higher boiling points and melting points than similar substances that cannot. But this is just emphasizing, so even the strongest intermolecular force is nowhere near the strength of chemical bonds. So it's only 2 to 3% of a covalent bond. So that just puts in context how much energy it takes to break a bond versus just doing the state changes. But that also makes sense though, because then if you were boiling your water, then it might just decompose or something if it was that easy to break your covalent bonds. And so now we're comparing, so ethanol versus dimethyl ether. And so again, we could let's look up the dipole moment for ethanol. Let's see, Wikipedia gives it to us. So ethanol, the dipole moment is 1.69. And what was it for dimethyl ether? So dimethyl ether is 1.3. So again, just so we can compare. And so kind of similar dipole moments, same masses, except what it explains a huge difference in their boiling points again. So we have a boiling point of 78 compared to negative 22. Yeah.
Where the hydrogen is located?
Exactly. So it's all that hydrogen bond again. So it's that hydrogen's directly bonded to that oxygen. So that means you have hydrogen bonding, and that makes all the difference. So this has an H bond, and this has no hydrogen bonding, so only dipole-dipole interaction, and of course London dispersion. While as ethanol has hydrogen bonding, and of course also dipole-dipole, and also dispersion. But of course the hydrogen bonding is what's dictating its boiling point. So now looking at this for a second, so take a minute or so. So what dictates the funny trend in this chart? So what's the oddity? Where does that come from? So what do you notice about this chart? So what is it even comparing? What is it trying to do? So we're comparing different groups, and then, so notice we also care about the mass. So if we think about the groups, did I forget? I think I didn't put a periodic table. But if we think about our periodic table, so of course, right, our mass is going to be increasing as we go down a group, so obviously as it gets bigger. And so we look at group 4, it seems to follow this nice trend, at least roughly. So we have increasing molar mass, means increasing boiling point. But then what happens with group 6? So what's the oddity in group 6? So which compound doesn't follow the trend? Let's start with that. Yeah, so oxygen or H2O over here. And so why does this one not follow the trend?
It only has one oxygenation state. Like, it's usually one of the ones that like another two.
So that's correct, but not relevant here.
Okay.
What do you think?
Following like the dipole hydrogen bonding, like the strongest.
Yeah, so this one, right, is the only one with hydrogen bonding. And so that could be a little confusing too, because you're looking at this group 6 and they're all the same, you know, geometrically. We've looked at that. So H2O looks like just sulfur dihydride and selenium dihydride, except there's a huge difference in their boiling point, all because of that hydrogen bonding. And that just goes back to, again, that effect with oxygen, nitrogen, and fluorine. Oxygen is just really electronegative, stripped off the hydrogen. Now we can have that hydrogen bonding. And again, you can just see how relevant it is. And then, of course, the rest of group 6 follows that trend still, and they do not have hydrogen bonding. They're just following their trend. And so I would expect to potentially have to explain this chart on an exam. So I would just give you this chart and then say, like, explain what's odd about it. And of course, you just point out H2O doesn't follow the trend because of the hydrogen bonding, which none of the others have. And so now that we know how to classify things by their different intermolecular forces, we can tell how strong their bonds are between our molecules. So this also dictates a lot of other properties. And so one of those properties is surface tension. And so you're probably familiar with surface tension. Did you ever do this in like a high school or middle school maybe, where it's like how many drops can you fit on a penny? So some people have. And so the whole idea is, I never know if we should do this in lab because it seems so simple, but it might be fun. So if you use water, right, you can fit a lot on there since that water tends to bubble up. And so we just learned, right, water has a bunch of hydrogen bonding forces. So that means it really sticks together. So that's why when you drop the water on the penny, it tends to start beating up and forming that big bubble because it's all holding itself together. But then, when you did this experiment, did you do like another solvent with it or just water? Water and soap? Yeah. That's a funny one. Well, maybe we should do this in our lab one day and compare it, because I was curious if you compared it to like an organic liquid. And so if you would put, they're comparing it to benzene here. So benzene, let me draw it out so we know what it looks like. So benzene looks like this. So of course, no hydrogen bonding. It's just a bunch of carbons and hydrogens in that flat. It's a planar molecule too. So it is a solvent, so it's a liquid. But if you were to try to beat up like benzene, although you probably wouldn't want to play with benzene, benzene's carcinogenic, but like pentane would be a good one, or ethanol. So if you try to drop like pentane on, so you wouldn't do very well with pentane since it doesn't have those strong cohesive forces, and so you just get a small bubble on there. And so again, so surface tension is just a property of liquids that results from the tendency of liquids to minimize their surface area. And so the surface tension of a liquid is the energy required to increase the surface area of a given amount. And so all we want to take away from this is, again, higher intermolecular forces just means increased surface tension. So with water, we know it has hydrogen bonding, so it has 72.8 for its surface tension compared to benzene, which is just 28.
So, regarding the last slide, the slide before that one, are the only elements that can form hydrogen bonds is oxygen, nitrogen, and fluorine?
Yeah,
Okay.
yeah, so write it down somewhere. It's just oxygen, nitrogen, fluorine. So those are the only ones that do hydrogen bonding.
You said higher surface tension is higher of the forces, the intermolecular forces.
Yeah. So greater surface tension means greater intermolecular forces, exactly. Oh. And there it is, it said it again. So stronger the intermolecular forces, the higher the surface tension. And then of course, if you do something to perturb that, so if you raise the temperature of the liquid, you start introducing more molecular motion. So that's going to start disrupting, right, your intermolecular forces. So that would reduce its surface tension. And so the surface tension also explains why you can float things that are technically less dense than water. So you can float a paper clip. So of course a piece of metal has a greater density than water, but if you have enough surface tension between them, then you can of course float, or like the little bugs that walk on the water, so they do the same thing. There's just enough surface tension where the bugs can walk across. So then the next property that's related to our intermolecular forces is called vapor pressure. And so vapor pressure is just the pressure exerted by a vapor when it's in dynamic equilibrium. And so the way I think about this is, so if you guys have ever consumed like alcohol or something, like you open up that fresh bottle and then like the ethanol hits you in the face, basically. I don't know if anyone knows what I'm talking. Some people do. But so that's vapor pressure. So you have your liquid, but there's going to be some, and that's that dynamic equilibrium that it's talking about. But you're going to have some molecules that are not in the liquid state. They're in that gas state. And again, that's that vapor pressure that you get. Usually I also reference, I don't know if anyone has worked with like diethyl ether though. So the ether is just a really low boiling point like we've been going over. But if you open up like a can of ether in the summertime, you'll get hit with like a face full of ether too. And so now with vapor pressure, the weaker the attractive forces between the molecules, the more molecules will be in vapor. So that makes sense, right? So you have weak attractive forces, so more of them are going to float off randomly, and so that gives you that high vapor pressure. So that's why I was kind of referencing, like the ether will give you a big hit since it has weaker molecular forces and like water. And so again, back to the alcohol, that's why you kind of notice it with the ethanol, but water is not going to really hit you in the face with any vapor. And so the higher the vapor pressure, the more volatile the liquid. And so like that's also why we saw pentane. So pentane would be considered, kind of more volatile. It's lower boiling. And so now let's look at this chart here. And so now this is just vapor pressure versus temperature. And let's orient ourselves on this chart here. So we have vapor pressure in torr. And then normal boiling point, again, we said this was at normal conditions. And so normal conditions is going to be 760 torr, which if you remember is 1 ATM. So just regular 1 ATM and then probably 1. And so we see with this graph here, so all this is showing is, okay, we increase the temperature, and then the point at which the vapor pressure is basically 760, then that gives us our boiling point. So once our vapor pressure is at 1 atm, that means that our substance is boiling. And so this is just comparing different boiling points so we can see this is that diethyl ether that I kept referring to that would hit you in the face. So that has 34.6 degrees Celsius, so relatively low boiling point. And then we mentioned ethanol or alcohol, so that has a boiling point of 78, and then of course water 100. So does that make sense for vapor pressure? And then our last section is going to be our energetics of melting. And so when high energy molecules are lost from a solid, the average kinetic energy is lowered. And so if the energy is not drawn back into the solid, the temperature of the solid will decrease. So melting is an endothermic process, and freezing is exothermic. So melting, if you want to melt something, you have to put energy into the system. So freezing, right, that heat has to go somewhere else. And so again, melting requires input of energy to overcome the attractions of molecules. And so now there's two different things on the heating curve that we care about. So as we just heat a solid, the temperature increases linearly until it reaches the melting point. And so this is just our, how much energy does it take to melt something. So this is not doing a state change. So this is just heating or cooling a substance. And so this is just a generic formula. So this would be the mass of whatever substance you're interested in times. So this stands for specific heat or heat capacity. You could find the heat capacity of a substance and then multiply it by its temperature. So that gives you how much heat you had to put in. And then once your temperature reaches a melting point, so then we started off here with this Q equals mass times specific heat times delta T. And then once you get to the state change though, so once the temperature reaches the melting point, all the added heat goes into melting the solid. So you saw this with your little wax melting curve that you made. So you're doing the opposite, but same concept. So you had your liquid, right, you were stirring it, and then you noticed, right, where your temperature kind of plateaued, and that was, again, where your state change is occurring. So, of course, with y'all's instance, it was solidifying, so going from a liquid to a solid, but that was doing the state change, so that's where all the energy was. So that's where, again, you notice the plateau, the temperature stayed constant, your substance did the state change, and then, of course, it continued on dropping. And so once all the solid has been turned into liquid, or, you know, in our case, we're going a liquid to a solid, then the temperature can rise again, or like we saw, will continue to decrease. So obviously we're looking in the forward direction in this case. And so the question is, well, how do we get the energetics then of melting? And so the heat of fusion for any substance is just the amount of heat energy required to melt 1 mole of the solid. And so you would look up this value, heat of fusion. These are just some heat of fusion values. And so you can right away see that our fusion is less than our vaporization value. So fusion, again, is just with melting or solidifying. So melting, or going back to a solid, so vice versa. And so melting is always endothermic. And so again, that means that solidifying or crystallization would be exothermic. So the opposite, crystallization. exothermic. And so our delta heat of fusion is always positive, again, going in the forward direction. And whatever energy it took to melt it, that's the same energy for crystallization. And obviously we have that negative sign just showing that the crystallization would be exothermic, so that would be negative since our heat of fusion is positive. And so that means that our heat of vaporization is for our gas, so going from liquid to gas, or vice versa. So of course, if we were going in the opposite direction, then we'd have to lose our heat of vaporization. And so you can just see how much greater that vaporization is. So much, much greater. That makes sense, right? Trying to get something from now the liquid to the gas state. And then if you're ever asked about sublimation, so do we know what sublimation means? You want to tell us? Nathan? Yeah. So anybody else know what sublimation? Remember? So that's when something, so think of carbon dioxide or dry ice. So dry ice is when something goes straight from a solid to a gas state. We've also seen this, so iodine tends to sublimate. So iodine starts off as those crystals, but then it makes a gas and then resolidifies. But if you ever see a problem asking about sublimation, you can find the delta heat of sublimation by just adding the fusion plus the vaporization, and that'll give you your delta heat of sublimation. All right, hopefully, so I'm going to kind of rush through this. We can always go through it again. I apologize. And so now let's go through what it takes to heat up water. So let's just see where we're going, where we're starting. And so we want to melt 1 mole of water, or we want to take 1 mole of ice. So we're going to start with 1 mole of ice at negative 25 degrees Celsius. And the goal is to take it all the way up to 0.5 here, and to turn it into a vapor, I think of 120 or 125 degrees Celsius. And so to do this, we have to break it down into the 5 individual steps. And so let's look at these legs. And so the first leg of this is just to heat up our ice. And so this is where things can, you just have to watch your units on all of these. And so things can get a little tricky with that. And so we start with our formula though. So Q is equal mass times our specific heat times delta T. And so you'd have to look up or be provided the specific heat for ice. So on an exam, I'd probably give you the specific heat so you're not scrambling on all over trying to find something. But then you just plug in everything. So we have 1 mole of ice. So 1 mole is of course 18 grams. So that's all that was plugged in here. So 18 times, so ice has a lower specific heat compared to water, so 2.09 joules per gram degrees Celsius. Then multiply it by your change in temperature. And so in this case, we went from negative 25 to 0, and then we had to stop there since this is where, right, our phase change is going to occur. So we just took it from negative 25 to 0. So we had our delta T of 25. And so you'd plug all that into the calculator. So notice the units of joules. And so the answer you would spit out is 941 joules. So then that brings us to our melting curve. And so the melting curve, and this is where I would refer to, oops, that's not what I want to do. Refer to your heat of fusion. And so your heat of fusion value, it should be given to you with 1 mole. But again, you'd want to like double check your reference. It could be given to you in some other unit. But then you would just multiply it by the number of moles, or if your heat was given in like grams and you want to convert it to grams. So just kind of make the unit make sense. So in this case, we have the heat of fusion is 6.02 kilojoules per mole. So by dimensional analysis, we know we just need to multiply by our molar amount. And so that's all they did here. So it took our 1 mole, multiply it by our heat of fusion, so 6.02 kilojoules per mole, to give us 6.02 kilojoules. So that's the melting. So then we melted it. So we went from ice, now we're at to liquid. So now leg 3 here, we have to take it from water that's at 0 degrees Celsius all the way to 100 degrees. So our next state change. And so that's all that is shown here. So now we're going to heat 1 mole of water from 0 to 100. So we go back to this Q equals mass times our specific heat times delta T again. And so plug in 18 now. Now we have to find our new specific heat. So this is for liquid water. And so that's 4.18 times 100. So now we're at 7.52 kilojoules for, again, just leg 3. So just heating up the water. Now we're at the boiling point, so it's time for another state change. And if we're at the state change and we're at boiling, that means we want our delta H of vaporization. Again, multiply it by the moles. I'm also basing it off of our delta H of vaporization. Multiply by 1 mole, so now we're at 40.7 kilojoules. And then the last segment, so we now have steam. Then we want to continue to heat that steam. And so let's look at that. And so the last bit, heat up our 1 mole of steam from 100 to 125. So again, you go back to this Q, mass equals specific heat times delta T, get your heat capacity for steam, and then just plug everything in. So 18 times 2 times our change in temperature, so 25, gives us 0.904 kilojoules. And then the last bit at the end, so then the question would be like, what is the total energy to go from, again, negative 25 degrees Celsius to 125 degrees Celsius from ice to steam. And so the last bit, we just have to add everything all up. And so if we go back to the beginning, so segment 1 was, and now I'm going to put it all in kilojoules, so 0.941 kilojoules plus 6.02 plus 7.52, oops, so plus 40, and then plus our 0.904. And so now we can say, well, it took 56.1 kilojoules total then for that entire energy transformation. So any questions about that? I know there was kind of a lot at the end. And we could probably do an example maybe on Monday and just look at one of these and kind of go through it. But do we at least kind of see the trend? So you notice you use this Q, mass 1, anytime we're just doing heat changes, and then we have to use our heat capacity or heat of fusion. So either heat of fusion or heat of vaporization for those state changes. And then this does get kind of confusing since, of course, for every element, and we'll do this on Monday, but like for gold, for example, if you want to do the same thing with gold, you have to look up the heat capacity for gold in the, like, you know, solid, liquid, gas state. So that can get kind of tricky trying to find all that information, but that's generally what you want to do. All right, so I guess we're out of time. We'll probably do another example on this on Monday, so everyone feels better about it. And then I will see some of y'all shortly in lab.